restoring force. The restoring force developed a spring.
Spring.
Okay. So the restoring force developed in the spring was given by the formula F equals Kx. Right? It is given by the formula F equals to minus Kx. Just once, if you are facing any network issue, so I can turn off the camera if it is required. Okay. So the restoring force, it was given by the formula F equals minus of Kx. And what did the value K represent here?
Where,
What does what does the value K represent?
constant.
Which constant? The name of this constant is, we call it as spring constant.
Spring constant.
So this is the spring K is spring constant. And what is the value X? Yes, what will be the value X?
K is spring constant.
K is spring constant and X is extension produced.
Their extension.
Yeah, X is the extension produced in the spring.
The F is force.
Yeah. Extension means, see, we consider these two cases. Yeah. So you have a spring and suppose this is the original length of the spring. We call this length to be L or L naught. This is the original length. We call it as L naught. Then if some mass is suspended from this spring, so this extends. There is an extension produced in the spring. If some mass is hanged from here, so some extension X is produced in the spring and original length be L naught. So the extension produced is directly proportional to the restoring force. And hence we obtain the formula F equals to negative Kx. The negative sign is there to just to intimate that force is opposite, restoring force is opposite to the direction of the extension. So this was what we had studied about the spring. Now one more concept over here. We started yesterday about the potential energy of spring. So how can we find out the potential energy of a spring? The potential energy of a spring. The potential energy means, is there any potential energy being stored in the spring? So first of all, uh, if we change the shape of the spring when we are extending it or when we are compressing it, so is there any amount of work done, or is the spring capable of doing some work? So as we discussed yesterday, that if you have a toy car or anywhere, so in the toy car you use a spring. Okay? That spring is being compressed by an external key so that it stores energy and hence it is able to do something. Okay, so the spring stores potential energy and we want to find out that potential energy. So the potential energy can be stored in a spring either by compressing it or by extending it. Okay. So in both ways we call it as extension only. Now to measure the potential energy of the spring, the potential energy of the spring is given by the formula. It's given by the formula 1 by 2 kx squared. The potential energy of the spring is given by 1 by 2 kx squared, where x is the extension produced and k is the spring constant. Okay, so we will do a small question again depending on this extension and spring constant. Okay, we'll try to find out the potential energy of the spring. We'll also do about the kinetic energy and then try to relate both potential and kinetic energies together. So see, okay, your question is find the extension produced in a spring if a mass of 75 gram is hanged from it. So, given that the spring constant is 300 Newton per meter. Okay. Also find potential energy stored in the spring.
Yes, sir.
So I think you will be able to do this. If you are facing any issues, just tell me. So try to recall the formula. Which formula should be used first?
W is equals to mg.
Okay, so we will be using F equals to mg or weight equals to mg. So we'll use the formula. Weight is equal to mg, but m will be taken in weight is equal to mg. M will be taken in kilogram. It's given in grams, so you need to convert it to kilogram.
0.
Yeah, how much?
0.075.
Yeah, 0.075 multiplied by g, that is 9.8.
9.8.
Okay. Also see, for your calculation purposes in your 10th class, you are taking a g as 9.10. So you can choose here also to take 10 if it's given in the question. If it's not given, you will take it as 9.8. Okay, so here let's give the value of g as 10. We are given the value of g as 10 meter per second square. So use 10. You will use here 10. You will get 0.75 meter. Now force we know, we can find out the extension.
Yes, sir.
Yeah. So use the formula. Which formula to be used?
F is equals to minus k.
Yeah, F equals to minus of kx. So you just use F equals to kx, find the extension. So we get F equals kx. And even if you use negative, so you will get x as negative, which means the extension is opposite to the direction of it. Okay. So force will be 0.75 equals k, which is 300, multiply x, which you want to find out. So it's 0.75 over 300 equals x. Now, since this we are using the SI unit, so this will be in meter. And if you convert it to
25.
centimeter, yeah,
25. 25. Put it down like that.
okay. So you get here 0.25 centimeter.
Yes, sir.
Just one, are you getting?
Yes, sir.
Now find out the potential energy. Find out the potential energy stored in the spring.
So
What is the
1 by 2.
formula for
Yeah.
So
So what
1
is
by
the
2.
formula for potential energy?
Formula of potential energy of spring. We just discussed that
Yeah,
potential
yeah.
energy is given by 1 by 2 kx squared. So it will be 1 by 2 kx squared.
Yes, sir.
Find out potential energy. Will be given by 1 by 2 kx squared. So this would be, you write here 1 by 2 multiply k, which is 300, and multiply x, which is 0.25 centimeters. So multiply with 10 to 100. Sorry, not multiply with 100, multiply with 10 to the power minus 2 or divide by 100. That's what you have. So it's divided by 100. Now you can find out this potential energy. Okay. Yeah. So I think you can calculate this.
9.375.
9.375. Okay. Okay. See, you will not, I don't think you'll be getting 9.375.
That is 9.375.
Hmm.
0.25 into 0.25 will be 0.0625.
Okay. So you'll get here 1 by 2 multiply 300 you multiply this, you'll get the answer. Okay. So obviously you will have here 100 multiply 100, and in the numerator you will get 0.0625. So something you will be getting in the powers of 10 to the power minus. You can write it as, of course, you can write it as 6.25 over 2 multiply 10 to the power minus 4. So you can divide it, you will get it. Yes? Yes, any problem?
No, sir.
Just 1 minute.
Sir,
Okay,
will
so
there be class tomorrow?
no, tomorrow you don't have class. You have class just today. Tomorrow you don't have class.
Okay.
Currently, I think your weekends are off, right? Are they off? But I don't know. But for physics, there is no class. So you have this. Hence, we obtain the work done, and we can get the potential energy. Okay. Now let's see. Try to do the same thing or similar thing, but using some concepts. Okay. Now I want to use some concepts and to have the level up of the questions. Okay. Before that, we'll just understand the simple pendulum. Yesterday, I tried to explain you about the simple pendulum. Okay. So how does a simple pendulum oscillate? We will see these two things, a simple pendulum, and we will see one more thing. So first of all, about the simple pendulum, we know that in a simple pendulum, if you observe a simple pendulum, so over there we observe change of energy. So how the change of energy occurs in a simple pendulum? So a simple pendulum is just a simply, it's pendulum. A heavy mass. It is a heavy mass hanged with the help of an inextensible thread. So you have an inextensible thread with the help of which a heavy mass has been hanged from the top. So see. So now how does the pendulum move? Observe its how it's moving. So we take the pendulum to this position A. Let this be position O and let this be the position B. So yesterday I told you that the positions A and B, they are the extreme positions. They are extreme positions, and the position O is called as the mean position. This position O, it is called as mean position. So what happens at the mean position? The object at mean position. If we take this pendulum to the either side, so at the position A and B, it has zero velocity. And when it comes back at the mean position, it has its maximum velocity. Suppose you take this pendulum to the side A, release it from here. So if you take this pendulum from here to this, take this from here to side A, release from here, so it will come, and as it moves towards this mean position, its speed increases. Okay. Now from this point O, as it moves up, slowly and slowly its speed decreases, and as it reaches the point B, its speed becomes zero. Okay. So in this way, this is how your simple pendulum oscillates. Now what we are observing over here, that at the extreme position, we observe here that at A and B, its velocity is zero, and therefore I can say its kinetic energy is also zero.
Yes, sir.
Its at the mean position, the maximum kinetic energy.
Yes, sir.
Just one
Sir, your voice is
minute. 1 minute.
breaking.